process words or sentences in RNN, how they are processed. It is very much and heavily inspired by StatQuest video of RNN clearly explained. So we are going to use the same architecture to explain this how the process happens in RNN. But a lot of times you will see the structure to be vertically. That is, it is input here, then there is RNN cell, and then there is output. So a lot of times you'll see the vertical structure, and then here hidden state arrow is going. A lot of time you'll see the vertical structure, but today we are going to draw horizontal structure because I want to do it the same way sir has done. So in this, basically what happens, first of all, let's make input. This is our input. Let's make the output. And then there is activation function in between. We use tan h. Okay, this is activation function has this written it. Okay, so this is activation function part. Here we have weights. Here we have weights. Star means multiplied. Let's multiply with weights. Add means add with bias, and then we get this output to calculate the tan h of it. We have separate weights and biases for output values, output nodes, and then we have a recurrent neural network, that is the hidden state. Hidden state fortunately also has weights. Okay, all the weights and biases, that is the only thing which is learned by the neural network. That is why we have the idea of weights and biases here. So today we are going to learn a lot of things. So this is our basic structure of today's RNN that we are going to use. So first of all, let's talk about the processing of the words. For example, I am giving these two sentences to RNN for it to be trained on these two sentences. So I love not you but myself, and I don't like myself. So how, first of all, everyone knows that machines do not understand language, they only understand numbers. So we are going to convert these words into vector formats. So first of all, let's see, we calculate unique words in both of the sentences. So how many unique words do we have? We have 5 unique words. One is here, second, third, this is repeated, fourth and 5, and then again this is repeated. So for suppose I is represented by this vector, and love is represented by this vector, myself is represented by this vector, and then don't is presented by this vector. Then we have like represented by this vector. So here is one more thing also that we are going to learn is how each sentence is processed. For example, we have this sentence S1, I love myself. In this, what happens, this neural network, now what is the idea of unrolling the neural network that we have read about a lot, or we have heard about a lot, that forward propagation through unrolling or through time, or backward propagation through time, or unrolling of the neural network. So let's learn about it. First of all, what we are going to do, we are going to process this word I. Let me show you how. So this is I, and this is our first timestamp, how the processing is happening. Now, I have plugged in some numbers here. There are some numbers, and then they are multiplied by weights. And the biases is added to them, and then we finally get few numbers. And still on those number we apply tan h. And then we have output weights. Let's write input weights and biases. Output weights, we multiply this thing with output weights and then add output bias to it. So what happens after the problem statement is I love myself. Basically, I want the processing of RNN works on the problem statement. So to process what's the sentiment, or to know what is the sentiment of this sentence, I'll need to know, okay, do I need output at every timestamp? So no, here I don't require outputs at every timestamp. So what I'm going to do, I'm going to ignore this output. So let's ignore it. I'm not going to consider this output, because after every word, I don't want to calculate the output, because after reading the whole sentence, only then the network is able to tell what is the sentiment of the sentence. So what will happen to the outputs that I've got here? So basically, they go, the arrow is go to this side. Now what is happening at this side? So this is timestamp 2, and we have the second input, that is love. And then here we have represented with number vectors. Then we added input weights plus. Then we add this hidden state. Let's suppose this is h naught. Basically, this is the output of the previous I input. The previous input output is called the hidden state. So whatever the output came from here, I'm passing it to the next input, and that is what we call as hidden state. And hidden state is nothing but context. Basically, how one word is connected to other word. So now I'll add this hidden context, that is this hidden h naught. Okay, so this is hidden thing I'll add. Then I'll add bias, input bias. But before adding that hidden state, we'll multiply it with hidden weights also. There are weights everywhere. There are weights for this input, weights for output, and weights for hidden state also. So we'll first of all add hidden state to it. And then we'll pass it on. So let's call it something else. Okay, let's write it down previous output. But it's technically not previous output, because it is multiplied with hidden state, weights of hidden state. So let's just mark it like this only. This output from this multiplication will be added with the love inputs calculation also. And then here also we don't require, here we'll apply tan h after adding this, after multiplying this, and after adding this to this, and adding bias as well. And we don't require output here also, that is why we are going to ignore this thing. Then we are going to pass it to the next input. Whatever the output we got from here, we are first of all going to multiply it with the weights of hidden state, and then we are going to pass this output to the next word, that is myself. Here also we got some numbers. Here we are first of all multiplying it with the input weight matrix. Then we are adding this output from the previous word. Okay, and then we are adding bias to it. After that, we get a number, we apply tan h over it. We'll learn why we add why we calculate the tan h of the outputs. And then after that, I don't have any more words to process in my sentence, because what was the sentence? The sentence was, just a minute. Yeah, the sentence was, I love myself, and now I don't want to output, and now I don't have any other words to process, so I'll calculate the output here. First of all, it will also be multiplied with weights output, and then bias output will be added to it to calculate finally to go in the output cell. Output cell will also have one activation function. In the case of sentiment analysis, it's always sigmoid. No, not always. You want to, if my sentiments are only positive or negative, then only I'll apply sigmoid to it. And then we finally have whether our sentiment, if it is close to 1, we consider it as positive sentiment. If it is close to 0, we'll consider it as negative sentiment. So I really hope that you were able to understand a bit about this, how the processing is happening. So I'm just giving you brief one more time. So first of all, I word is processed. After processing the I word through input layer through RNN cell, then we pass this output of I to the other word, that is love. And before passing it, we multiply it with hidden weights matrix. After that, love word calculations are calculated, and then we also get one output from the word love. We pass that output to the next word, that is myself. We do the calculations, and then it is moved forward to the output output node or output layer, instead of passing it through hidden layer, because we don't have any more words in our sentence. And then we get the output whether our sentiment is positive or negative. So this was the first basic idea of how the processing happens. So basically what things are happening, so if my sentence has 3 words, the RNN will be unrolled. uh, this is second timestamp, that was third timestamp. My RNN will be unrolled 3 times. Or forward propagation will happen through 3 timestamps. Forward propagation through time will be 3. Forward propagation through time is 3. Now what if my sentence was I don't like myself? Here the here then the RNN would have unrolled 4 times, and there would have been 4 forward propagation through time, because there are 4 words in the sentences. That is the biggest advantage of RNN. Now if you notice carefully, we are just copying this same thing, this same architecture, once again, then once again, and we are just activating layers according to it. We did not activate output layer here, we did not activate output layer here, but they are all are being copied 3 times. Basically this thing is copied 2 more times. So if it is copied, that means whatever the weights and biases are here, they are going to be carried forward here and here as well, here and here as well. Same goes for the hidden state, because this layer is being passed again and again, or this layer is being used again and again for the connection. So here hidden weights will be the same. In total, That is why RNN has shared weights and biases. RNN has shared weights and biases. Excuse me, please, if you hear any noise. Yes, I think it's better. So yes, we got to know about RNN has shared weights and biases. Now let's calculate the total number of weights and biases it has. Mm, so we are calculating trainable parameters. Here our input consists of how many nodes? So my word is represented by 5 nodes or 5 numbers. So my input is going to have. Why my drawing is so bad? I should pick another color, right? Yep, purple is good. This is going to have 5, 1, 2, 3, 4, 5. And then RNN cell is going to have you can keep it how many you want, how many nodes you want the RNN cell to have. I want it to have 4 nodes. And then output node fortunately will only have one node because it is a binary class classification. So it's either yes or no, sorry, positive or negative. Now let's connect everything to calculate number of weights and biases here. Oh, I also forgot the hidden layer, right? Hidden state. What am I even saying? This is hidden state. Yeah, we were drawing this. So feel free to skip video or increase the speed of it if you don't want to see this diagram or drawing. Let me make it real quick. So let me make joint connection here also. So basically this, which color should I choose? This one node is passing weights to how many nodes? 4 nodes. So this one node is getting how many values or how many connection? It is getting 5 connections. Similarly, here it is also receiving 5 connections. Here also 5 connections. Basically, I'm talking about this. Here also 5 connection. Or I think you'll all will misunderstand. So let it be. It is receiving 5 connections. It is receiving 5 connections. It is receiving 5 connections. It is also receiving 5 connections. So 4 times 5, we have 20 weights. And biases are always divided with how many nodes do we have in RNN cell. Okay. So we have 4 nodes in RNN cell. So 4 biases are there. Here these are connected. So it is only getting 4 connection. We only have one node here and it is getting 4 connections. So here are 4 weights. And then we have one bias because there is only one node here. Now for hidden state, it how many weights? First of all, hidden state does not have any bias, thankfully. So how many weights does it has? So basically all these cells are connected back to this own thing only. So there is just reverse connection here, here and here. So I'll tell you how many hidden state weights are there. So how should I explain? Just a minute. Okay, let's explain it through the shape. You'll get it better by when I'll start describing, or we are going to calculate the shape of those weights and my matrices. Yeah, let's pick some another color now. Here input weights will be how many? 5 cross, sorry, 4 cross 5. Input weights are 4 cross 5. They are represented by 4 cross 5. Okay, total 20. And then we have bias. What will be the shape of bias? It will be 4 cross 1. Okay, and then just a minute. And then we have this RNN cell, which also has 4 nodes, and we have to calculate the hidden state weights. So that it passes on to another it passes the hidden state to another input. And then we have here weights. Output weights will be 1 cross 4 and bias will be 1 cross 1. Then only at the end you will get one output. So if for the basic matrix multiplication, when you multiply input here, let's do it. This is input weight, okay, it is happening in input weights times input, which is of length 5 cross 1, plus let's do what is the answer of this thing. So when for the basic matrix multiplication, this and this is same. If this and this is same, then only we can do the matrix multiplication. So whatever output do we get is of the 4 cross 1 shape. And then we add this bias to it, which is 4 cross 1. Then the output from here is also 4 cross 1. Am I right? And now this output will be passed on to the then tan h will be applied to it. Basically tan h is applied element wise, so after tan h we still have this same output with the shape 4 cross 1. After that it goes to hidden state. Now since this is 4 and we'll have to multiply this hidden state weight matrix with this answer to calculate a hidden state. So if it is 4 cross 1, then it should have 4 number of rows. And if it has 4 number of rows, at the end what output do I need to add it to another layer or another input? It should be 4 cross 1 only. So to reach hidden state output, so that hidden state output comes shape is 4 cross 1, we'll have to make this a square matrix 4 cross 1, or you can say it these connections are being made one by one. So you can say hidden state layer has 4 nodes and these are connected among themselves. Okay, I'll show it in the calculation in the next video how this is done. So to basically maintain the shape of the input processing of the word, we'll have to keep it a square matrix. To maintain the shape of the output, we'll have to keep the weight matrix, hidden weight matrix, as a square matrix. And it's depend upon the number of nodes in the RNN cell. If the number of nodes in the RNN cell is 4, then the weight of hidden matrix shape is, hidden state weight matrix shape is 4 cross 4. So the output comes out to be 4 cross 1 next time after the hidden state. Or if we do not wish to calculate the hidden state, so we got to know, okay, what is the shape of the uh, hidden state weight matrix? It is 4 cross 4. So in total, let's write it down here. Summary: total number of trainable weights and parameters in RNN cell. Just a minute. So for input, we have input weights and input biases. We had input weights to be 20 and biases were 4. Then we had RNN cell. In that we had 4 nodes. So RNN cell didn't had weights of it. In RNN cell we get a hidden state. So what was the hidden state? Only has weights and no biases to it, because it is being connected to itself only. I'm not able to represent it properly here, but it is being connected to itself. That is why it does not have bias. It only has weights. And which shape is 4 cross 4 was the shape of the matrix. So 16 weights, hidden weights, and biases. So there was no biases. And then output had 4 weights and 1 bias. So in total, if you add all of these, 24 plus 4, 28 plus 1, 29 plus 16, it's 45. So we have total number of trainable parameter is to be 45. Now I am leaving you with the question. If you have 7 nodes in your input, and 7 nodes in your input, in RNN cell you have 5 nodes, and in output you only have 1 node. How can you calculate what will be the hidden state? Let me add the hidden state also. Yep. What will be the shape of, what will be the, you can also tell the shape or input weights. How many will be the input biases, how much will be the output weight, how much will be the output bias, and what will be the size or value, total number of hidden weights. Thank you so much for watching this video.